Start the review for this. The students in next section. So the students for the next section, I'll go over for them. They'll be getting this, but since you know, you don't, this is your class before your exam. I'll be going over your practice exam now. Okay, so on this, there will be 105. I just didn't total them up to 105 over here. Again, so there's 5 points of buffer built into the exam. It is going to be a lot of pages, but a lot of these questions are like one problem per page, right? So that you have plenty of room to draw, right? So keep that in mind. I've put in the basic string functionality. I don't think you need to know those. So the whole substring starts with methods that you typically have. There was a quiz by the way. So ask somebody else for the password. So say. There's also going to be the map. I'll put down, map has put, get, contains key, contains value. Those are going to be the only functions you need. And then a reminder of what the tree functions are, which you shouldn't need. You shouldn't need to be able to call. You shouldn't need to call the add method or remove method or the contains method for any of the tree methods we're writing, right? Okay. So the first page of your exam will look pretty much exactly like this. The only thing that will be added is a sentence over here that says, right over here, that says you may justify your answer with 1 point. For instance, you might say, you might put down linked list instead of stack or queue for something, right? Because you can use a linked list wherever you would want to use a stack or queue, right? And so long as you justify your answer, you can get credit, right? So if you're not sure about something, but you think there's a pretty good argument to be made for it, right? Justification, you're probably going to get at least a point. But you can also just leave it with the data structure if you're pretty sure about this. And you'll want to just choose something over here. Notice that heap isn't a choice, but priority queue is, right? You use a heap to build a priority queue. So our choices are array list, linked list, stack queue, tree, priority queue, set, or map. There will probably be something like this on the final exam as well if I get my way. So with albeit a lot more entertaining questions. So I do like to find these answers quite entertaining, and if you play some collectible card games, you might actually come up with an advantage on this exam. So, all right. So you need to model which patient should be seen next at a hospital. Patients should be seen in as close to the order of arrival, but patients with a more severe situation should be seen first. So what kind of so what kind of data structure should this be? Yeah, priority queue, right? Because people are waiting in line, but people get a skip in line if they've got if they're depending on what their situation is, right? Right. So anything where you're waiting in line, but people get to skip because of a certain status, right? Whatever that status may be, being more important, being in a way worse condition.
Like it allows for custom comparison.
Yeah, it's just basically anything where you need to reorder this, where queue needs to reorder, that's a priority queue. Okay, a router needs to hold packets in a buffer and deal with them in the order they appear. So what is that one? That's just a queue, right? Because you get in packets, you deal with them as you can, and right, hopefully you empty out that buffer. This is pretty much a classic thing that a queue is used for. Okay. You need to model a hierarchy. What data structure is appropriate for that? Tree. Notice that I said that it's a tree, not that I put tree over here as opposed to binary search tree, right? Yes?
What's the answer for queue again?
Queue. All right. And you need a data structure to hold your previous decisions in case you need to backtrack. Yep, stack, right? A clear sign that you're going to be in trouble this exam is if you answer recursion there, which I've had happen for a similarly phrased question, right? A stack is a data structure that helps you perform basically recursive-like functions. So if you need a backtrack, then you want to use a stack for that. All right, on the actual exam, this will appear a bit differently. It will be worth 10 points, but it's essentially going to be, on the actual exam, essentially this page, the next two pages kind of get combined. I will be giving you a tree, and I'll have a tree diagram, and I'll be asking you, like, specifically about this tree. What is the relationship between these two nodes? Is this a full tree? Is this a complete tree? Those kind of things, right? So I'll give you a tree, and you're going to ask some basic facts about it. Here, so fairly good mapping over here. All right, with one wildcard question over here. So The node at the top of the tree is called what? Root. Yep. The links from a node to its successor are called branches. If you had smart aleckly answered the word, put in the word links there, I would have given it to you because they are also called links. Right? So the predecessor of a node in a tree is called what? The parent, right? Not, and here I wouldn't have given you predecessor because everybody calls it their parent, right? Nodes that have the same parent are what? Siblings. Yeah, siblings. Siblings. If you call them brothers or sisters, fine too. Everybody understands that. Right? If I ask you, for instance, if we've got this node, right? If I've got this guy, and I'm in this situation over here. So let's say I've got node A, and this is node B, and I want to know what the relationship between what is B to A, right? How would you describe node B to A? Node B is A's what? Uncle. You say that, I'll be perfectly happy with that answer, right? You can grab any of those relationship terms that you want. What about as far as node C, if you put grandparent, if she said grandparent of A, I'll accept it. The more generalized term is ancestor, but hey, I mean, if it grandparent is easy for us to understand. So there's no need to go too crazy about that. All right. So now describe without using code how to calculate the height of a tree recursively. So what is the height of the tree first off? What is the height of a tree? Well, what's the height of this tree? 3. Yes. So it's 3. And that's because it's the longest path from the root to a leaf is 3, right? Now, how can you calculate the height of the tree recursively? Right? Well, what's the height of this of this subtree over here?
1.
Yep. What is the height of this subtree? 2. What's the height of this subtree?
1.
Right? So C's left side is height 2. Its right side is height 1. Right? So its longest path of its child is 2. So the way I can kind of figure out the path is, well, first off, if I'm empty, right? If I don't exist, if I'm a null tree, then my height is 0. But otherwise, I'll get the height of my left side, I'll get the height of my right side, and I'll figure out which one is bigger. Does anybody know a function, by the way, that given two integers will return the bigger integer? Yep, there's a max. So there's a math.max function, by the way, in case you need to do that. If you give math.max 2 arguments, it will return the bigger argument. So I figure out which is the bigger of my left side or my right side, right? So I recursively calculate the height of my left side or right side, and then I return the bigger side plus 1, right? Because my height will be the bigger of my left or right plus 1. If they're tied, it's the same. Make sense to everybody? Right? So, may or may not be useful. All right, so here, draw an example of each of the following types of binary tree. Use a different example for each possible tree. And the reason I put that clause of use a different example is because I could draw this, right? I could draw this. And that is a full tree. It is also complete, and it is also perfect, right? So that's why I said to draw a different type. So what does it mean to be a full tree? What's the definition for full? Yes?
Every node has 2 children or no.
Yep, every node has 2 children or no children, right? This guy has no children, so we're a full tree, right? This is not a full tree, however, because while this one has no children, he has 1 child. If I were to do this, it is now full, and it is also complete, and it is also perfect, right? We'll go into complete in a bit more detail, by the way. Right? This is also full because every node has either no children or 2 children. It's fairly straightforward to figure that one, to figure this one out, right? So everybody has either 2 children or no children. Okay? So Complete trees are actually the easier one to do than complete. Sorry, perfect are easier to do than complete, so we'll go ahead and do perfect first. A perfect is a tree. A perfect tree is one of height h, and you have 2 to the h minus 1 nodes in it. Now, in practical terms, that means that the tree essentially is filled at every level. Is that basically it's filled and completely symmetrical on every level, right? Completely filled and completely symmetrical, right? So this is a perfect tree. This is a perfect tree. Right, this is the perfect tree because it's height 3 and it has 2 to the 3 minus 1 nodes in it, 7 nodes. Right? Notice that's like completely symmetrical. Oh, and they're always going to be full. Right? Over here, this is 2 to the 4 minus 1 nodes, right? And for it to be a perfect tree of height 5, we'd have to draw basically 2 children for every one of these leaves, right? All right, so that gets us into the question of what is a complete tree. Complete trees are perfect for so let's go ahead and talk about we'll go ahead and go with this. This is an example of a complete tree. Now this is a complete tree. It's height 4, but for height h minus 1. Basically, for every level but the bottom level, it's perfect, right? Everybody see, except for the bottom level, it's perfect, okay? But for the level underneath it, it follows a special rule. You can have as many nodes as you want, so long as they're all filled going from left to right and there's no gaps. So, for example, this is a complete tree. If I were to draw something over here, a node over here, this is no longer complete because it is no longer filled in left to right. There's a gap there, right? See how there's a gap there? If I drew, on the other hand, a node here, that's complete. It's still complete. This is no longer a complete tree, right? No longer complete, no longer complete. Oh, it's complete and perfect, right? If I erase this, this is now, again, better? It is now, complete. Okay? So complete fills in left to right. And the reason this is important is because of the heap data type, right? I'll just go over here for these guys, right? If we're using the heap, right, the underlying array, right, this is index 0, this is index 1, this is index 2, index 3, 4, 5, and index 6, right, for the underlying array. This would be index 7, right? Index 8, and basically, so long as we have no gaps, that means we have no null values in the underlying heap, right? So a heap basically, a complete tree perfectly maps to an array for storing a tree. So that's why it's kind of valuable to have a complete tree. All right. All right, so again, this question and this page and this page are going to be folded together on the exam. So pages 4 and 5 will be folded together on the exam, worth 10 points. This page, you're going to get a page exactly like this on the exam. It will ask you, it will just ask you different numbers. Draw a tree, and what you're going to do is that you're going to insert these items one at a time. I think it's a fairly easy question, but occasionally 1 or 2 students do get it wrong. Also, very unoccasionally, a student makes a very simple error and they just simply transpose a number in the wrong place, and they just roll with it. Whatever. We deduct a point for something where they wrote a number and they thought it was supposed to be 47, but they put 74 or something like that. We deduct a point and we move on, right? It's no big deal. You just made a minor mistake, right? That doesn't really matter. So the way this one would work, let's see. Right, so the way this question works is draw the binary search tree that forms when we insert these numbers. So the first number we insert, and it's going to be, the root is 42. I'm not sure if I redid these from last time. Then we insert 10. So 10 is smaller than 42, so we go to the left. 50 is greater than 42, so it goes to the right. 12 is less than 42, greater than 10, so it goes over here, so it goes left, then right. Then 17, less than 42, greater than 10, greater than 12, so it goes over here, right? And don't worry if your tree is drawn horribly. Mine's probably going to be drawn horribly, right? It doesn't need to be the most beautiful drawn tree ever. I let LaTeX do that for me if I need to draw beautiful trees. 17, so 80 is greater than 42, greater than 50, so 80 will go over here, right? Negative 12 is less than 42, less than 10. Okay, 100 is greater than everything you've seen so far, so it's greater, 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 so it goes all the way to the right. Right? 96, greater, 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 less than this, so 96 goes over here. 105, 86, so greater than 80, less than 100, less than 96, so 86 goes over here. And then 72 goes over here, right? It's fairly straightforward, right? You're more likely to make a simple mistake than to not know this one, right? And if you make a simple mistake, like I said, no worries. We're going to count it like a simple mistake, right? Like a point, okay? We're not. It's when we get something that doesn't make sense, like you completely forgot how binary search trees work. The important part being search there, right? When somebody doesn't understand this, it makes it very obvious, and I keep it on because occasionally there's 1 to 2 people per semester. Don't be that person, right? Okay. Now on the actual exam, what you're going to get following this page. So on the actual exam, what you'll get following this page is I'll ask you to do some traversals of the tree you just drew. Okay. On the actual exam, once you're done with that, the way I'm going to ask you, do you know your traversals, is that I'll ask you to do a traversal of whatever you just drew. Okay. So there you go. That's some insider info. On this practice exam, I tell you just go ahead and let's move on to the delete function. For the delete function on the actual exam, what happens? For the delete function, I tell you that on the exam, I instead give you a tree I drew and ask you to delete nodes from it, right? Now, the safest thing you can do, by the way, since you're not working with a dry erase board, by the way, is to, although it might be tedious, if you delete something and it wasn't a trivial deletion, like deleting something with 1 child or 2 children, you might want to redraw your tree in between deletions so that we can give you partial credit in case you made a major mistake along the way, right? Okay, so the deletion is where more people lose points because they forget how to do a deletion. So delete 42 from this tree, right? So we're first going to delete 42 from this tree. So how do we delete 42, right? It's the root. It has 2 children, right? So what we have to do is we have to find the smallest, its in-order predecessor. Or you can do the next in-order successor, but I'm going to go ahead and do the in-order predecessor, which is the biggest item that's smaller than it. So that, and how do I find that? You go 1 step to the left, you go all the way to the right, right? And then we just simply copy the value over and delete the value that we copied over, right? Fairly straightforward. So let me just go ahead. What if 17, though, what if it looked like this? 17, and then we had this. We had a tree over. What happens to this subtree over here? Where would that go if we delete it? Yes?
It gets adopted by 12.
It would get adopted by 12. Exactly right. So you just simply put that there. Okay? Now, to delete 12, what would we do? Well, in this case, if it was our original problem where 12 didn't have a child, right, we'd just kind of just erase it, right? Pretty easy, trivial to delete something that's a leaf. You just delete it. If we have to adopt something if 12 has already has one child though, then its parent adopts its child. Right? Now we got to delete 17, right? And I'll just go ahead and delete that because that's not going to make any sense if I can't keep that up there anymore. Okay, deleting 17. We have to find the biggest thing. We have to find the biggest thing that's smaller than it. So we go one step to the left. We go as far as we can to the right, which means we can't go anywhere at all. Right?
On the test, you assume that we would delete the original tree, not the tree that we modified.
Yes. Yes. So in the on the exam, you're deleting 42 from the tree, then 12, then 17, then 96. So it's the same. So you're deleting these things successively from the tree, right? So the changes. So once you make a change to the tree, it stays, right? You're not, redrawing. You're not starting from scratch each time, right? Was that your question?
Yes.
Okay. You're not starting from scratch each time. It works like this, where we deleted 42, then we deleted 12. Now we're going to delete 17. We go one to the left, we can go all to the right, way to the right. So we replace it with the value we're going to delete. Then we delete this value, and so that becomes deleting with one child. The value of deleting with one child, so, right, that gets adopted. Deleting 96, again. We find 96. We found it. We got to find this biggest thing that's smaller than it. Well, sorry, no, we don't, because it's one child. Right? So we just adopt. Right? If we have one child, that's an easy case where basically our parent adopts our child. Right? Okay.
What if you have two children?
If you have two children, you find the biggest thing that's smaller than you.
Then you just rotate it.
You don't do any rotations, right? If 96 had two children, right, say it had 97 as a child, and we're deleting 96, we'd go to the left, right, to find the biggest thing that's smaller than us, go all the way to the right, turn south to still be 86, so we replace 96 with 86, right?
Yeah.
Right. The entire point of this is that with the whenever we delete something with two children, what we're doing is that we're finding the biggest thing that's smaller than it, so that we don't really have to reorder the tree. We replace it, and then we delete that original copy of the biggest thing that's smaller than us. Now, why do we do that? Because it condenses our cases down from something complicated, deleting something with two children, to deleting something with one child. So, all right, so here is the traversal questions. Which of the following is a pre-order traversal of a binary tree? Which of these is the pre-order traversal? B? Yeah, B. Root node process left tree, process the right tree. Let's go ahead and do a pre-order of this. Right, pre-order traversal of this would be 10. Then I've got to do my left subtree. So it would be 10, then I would do my left subtree, which would be -12. Then I do my right subtree, which would do 50, then do its left subtree, which was nothing, then do its right subtree, which is 80, which would do its left subtree, which is 72, which would do its right subtree, which is 100. Then it would do its left subtree, which is 86. 86 would do its left subtree, which is nothing, then its right subtree, 97. Then we're done with 100's left subtree, so now we're on 100's right subtree, which is 105. Right? So, and now we're done with 10's right subtree, so we're done with the entire tree. Yep. So, all it means is just do yourself first, then handle your left subtree, then handle your right subtree, and you handle your children exactly the same way as you handled yourself. Now, which one is post order? Yeah. Post order is, C. You always do the left subtree, then the right subtree. So D was always wrong because you never do the right subtree first. So for post order, we do our children first, then ourselves. So here, I'm going to do, so we're at 10, we're going to do our left subtree first. Negative 12 has nothing else in it, so it's going to, we're done with our left subtree. Now we're up here at 10, again, but before we can process 10, we have to do our right subtree, which means doing, we're into 50, 50 is going to do its left subtree, then it's going to do its right subtree. Okay, now we're at 80. 80 is going to do its left subtree, so 72 is going to do its left subtree, its right subtree, then itself, 72. Then we're back at 80. Then we're going to do an 80th right subtree. We're back at 100. There's it down to 100 for the first time. Then we're going to go down to 86. We do 86 left subtree. Then it's right subtree, 97. Then we travel back up to 86. We're done with 86. Then we're back up at 100. We have to do the right subtree, which is 105. So down we're done with that. So we're done with 100. Now we're done with 80's left subtree and its right subtree, so we're done with 80. So now we're done with 50 left subtree and its right subtree, so we write 50. Where did 10 come from?
That was 100.
That was 100. Okay. I'm like, where did 10 come from? Because now we're at 10. Okay, there we go. That kind of stuff happens on exams. That's a point mistake. Don't fret about it, right? Where basically you write something down where you're meant to write 100 and you write down 10 instead. We understand why that happens, although you won't be able to understand why you did that later on. Okay. So you're going to also get this kind of question for heaps. It's going to be pretty much exactly the same kind of question for heaps as just with the different numbers, right? You can either present it as I say ignore the underlying array, but you can draw it as the underlying array if you want, right? But essentially the way this is going to work is that this works exactly like the tree problem, right? So we start with a blank slate. So the first thing, now remember with a minimum heap, the smaller items, they bubble to the top, and the heavier items sink to the bottom. So let's get started with this. All right, so first item that we get is 8. So 8 becomes the root of the heap. Then we insert 10 in the next possible place, which is this child. Then we insert 20. 20 is still pretty heavy, so there's no need for it to bubble up. You know, it's heavier than its parent, so no need to bubble up. Then, 50, still heavier. The next item is 20. No need for it to bubble up there. Then 1. So 1 is pretty light. It's lighter than its parent 10, so it needs to bubble up and swap with 10, right? So 1 and 10. But we're not done yet, right? We still have to go all the way up to the top, right? It doesn't bubble up until it's reached the top or until it's, until it's heavier than everything else. So 1 is lighter than 8, so 8 sinks down while 1 swaps up. 1's now at the top, so we can stop. Right? Notice that the minimum heap property is still maintained among everything. Now let's insert 4. 4 is heavier than 50, so 4 bubbles up and swaps with 50. Now we check 4 against 1. Is 4 lighter than 1? No, it's not, so it doesn't bubble up. So we stop here. And now we insert 3. 3 is lighter than 4, so 4 sinks down and 3 bubbles up. 3 is heavier than 1, so we stop. So this is the end result of our heap. Okay? You're going to get a question very much like this on the exam. I simplify it, though, on the exam to do a bit less drawing. So, but right now I'm going to answer this question here. Using the heap you just drew above, draw the heap that results after removing an element twice. Now, what is the only item you can remove from a heap? The root, yeah. You can only ever, when you do a removal, you can only remove the root of the heap. So how do we remove it? Yep. We replace it with the last thing in the heap. So we replace it with 4. So we replace 1 with 4. And now 4 Now we got to make sure that it sinks down into the appropriate location. So 4 is heavier than 3, so 4 swaps with 3. And so now, does 4 need to swap down furthermore? 4 is lighter than 50, so it doesn't need to sink down any further. Okay, now we do our second removal operation. We delete 3, and we replace it with 50. 50 is pretty heavy. So, in fact, it's heavier than both its children. So what do we do in this case? We always swap it with the lighter child, which happens to be 4. So 4, so it's heavier than both its children, so we swap it with both. So we swap with them. 4 and 50. And now 50's hit bedrock, so to speak, so it doesn't sink any further. All right? So that's how deletion works for this, right? Any questions on the heap?
Sorry, what are you removing second time now?
We were the root. We removed 3 because it was the root of the heap. We always remove the root of the heap, right? If I asked you to do another remove operation, you'd have no choice but to remove 4. That make sense to everybody? Yes.
And then we always replace it with our lighter child.
You always replace. So
we replace it with the last one, but then once it's at the top, we move it down with we switch with.
Yeah, if you're bigger than both your children, right? So, like in this case, if we were to delete again, right? We delete it. We replace 4 with 10, right? But notice that 10's only bigger than only heavier than one of its children, right? So we don't have to make any choices there, right? So we just simply swap that. On the other hand, say that we were in this scenario, right, where we had, let's see, it's a bit harder to come up with these scenarios. So we had 1, 5, 10, and 50 over here, right? We've got a heap over here. We're going to delete 1, right? So we're going to replace it with the last element in the heap, which means 50. And so now we've got to push down. 50 is heavier than both its children, right? So we swap it with its lighter child. And this is just so that the lightest child always moves, so that the smallest item always moves to the top when possible. Now, adding and deleting to a heap does take log time. As you'll see, we utilize this in heap sort, as you may have seen on the video. The only difference is that heap sort will use, and this is for future stuff, heap sort uses a max heap as opposed to a min heap. But as a result, because you're essentially adding n items to heap, removing n items to heap, it takes n log n time, and it's pretty fast. Although a lucky quick sort works faster.
Can we do another heap?
Another heap? Sure. Adding?
Removing.
All right. So give me reasonably sized numbers, something between 1 and 100. Okay. 52. 52.
73.
Yep. I'm just making sure that I'm on. 52. 73. We add 73 over here. 42. 42 we add over here. 42 is lighter than 52, so it bubbles up. Right? So we swap 42. And then we can stop swapping up 42 because it's got all the way to the top. All right. 12. 12 is lighter than 73. So 12, 73. And then 12 is lighter than 42, so it bubbles up there. 12 reached the top, so we're done. 75. 75 is nice and heavy, so it stays put. 6 is light. 6 goes over here. 6 swaps with 52. 6 is still pretty light. It's lighter than its parent, so we swap it with its parent. 1 is also very light. 1 swaps with 12. 1 swaps with 6. Okay. Do we want to add anything else to this heap? Where would the next item go? Left, yeah, but left of 73. All right, let's go ahead and add 5 to this. 5 would swap with 73. And then 5 would swap with 42. Okay? So how would this deletion operation work? How would we delete from this heap?
Take 73.
Yep, we take 73 and put it at the top. And then 73 is pretty heavy. In fact, it's heavier than both its children. So we swap 73 with the lightest child. That way, the lightest child does make its way to the top. Notice that 5 is, by the way, the smallest thing in the heap. So now that makes it the appropriate size. So 73. Now 73 is heavier than one of its children. Right, so that bubbles to its top. And that ensures, sorry, that was 42. And that ensures that basically in its subheap, the smallest item got to the root of the subheap. All right. So the next one, again, this will be pretty much look exactly the same on the exam, Huffman encoding. The only difference is I asked you to encode something here, and on the exam I'll ask you to decode something. Now, what's important to note is that regardless of how messed up you did your tree, your Huffman tree, your encoding tree, no matter how badly that went, right, we're still going to, for this part, when we ask you to encode or decode something, we're going to just still, run off as though you were correct, right? So these 2 points, so this and this will be independent of each other, okay? So, all right. So first things first, we need to draw our Huffman tree. All right, so I went ahead and said we need to encode a document which has these symbols, right? And we want to compress it so that it's nice and small. So we need to draw a Huffman tree with these symbols. Right? So the first thing we do is that we arrange these symbols into a priority queue by their weights. So with the smallest weight at the top of the priority queue. So X is 1. Right? X has a weight of 1. L20. So L20, then P40, then A50, and then E60. I do try to make the numbers easy to add, by the way. I do try to make them fairly easy to add, so nothing like 53 and 80, nothing like 53 and 87, right? That might cause an addition error. I try to basically make it as nice and easy to do as possible, right? So the rules for forming a Huffman tree is fairly straightforward. You take your priority queue, remove 2 items from it. Your first item, we call it the left item. The second item, we call it the right item. We combine them into a new node with the combined weight of both items and insert that into the priority queue. So, right, let's see how that works. X and L, right, we combine that. So X goes to the left, L is the right. We combine them into a new node with a combined weight of 21. Right? So this was dequeued, this was dequeued. We combine them, and we put 21 back into the priority queue. Now I'll put a dash to just remember what it is. Now the thing that we need to note is that here are the two mistakes that students make. They don't remember that it's always the first thing you dequeue goes on the left, and the second thing always goes on the right. That's the first mistake that we get from students. The second mistake that we get from students is now that we put it back into the priority queue, they forget that it's a priority queue. Okay? This means that this needs to rearrange. Now what happens is that in those cases is that that's wrong in one of 2 ways. The student always leaves it at the end, or they always put it back in the beginning. So, now in this case, we've already ordered this. 21 is smaller than all these things, so 21 skips back to the front of the line.
How does it do that in a parent thing? It's
What?
Like, I'm just trying to look at it as an index, like if it's at 3, right, 0, 1, 2, 3.
We're just putting these in order, right? We're just keeping these sorted.
Okay, so we're not necessarily.
We're keeping this in a human view for us, not necessarily a heap view.
Okay.
Okay? So now we've got the next two items, 21 and 40. So 21 goes on the left, 40 goes on the right of this new node. Or rather P, which is associated with 40. So they get the combined weight of 61, right? Notice that that's 1 plus 20 plus 40. And so now we re-enter, now we put this back into the queue. Okay? Right? And that's bigger than everything else, so it stays at the end. Right? So now we have A and E together. They're going to add together, and that's going to be 50 plus 60. So A, E, that's going to add together as 110. We reinsert 110, right, into our priority queue. Now we DQ twice. One's on the left, one's on the right. We combine them, and we put them into a new node with a combined weight of, well, it's the last node, so it doesn't really matter, but it would be 171, right? They get a combined weight of 171. But now we've got all of our items added to there, right? We know we're done when there would be only one item left in the priority queue. Okay. And now everything's in a tree. Okay? So this is this is the tree we use for encoding, right? How do we encode stuff? Well, we mark all the left branches with 0, all the right branches with 1. Okay? So how do we encode something? Well, to encode apple, and decoding is a bit easier, but let's go ahead and encode apple. Okay? Apple, we would encode it by noting that, how do we encode A? 1, 0. So we write down 1, 0. Then how do we encode a P? 0, 1. 0, 1. Another P, 0, 1. And then I might just simply do a visual indicator for myself, not necessarily for the professor, but for myself, just to make sure I wasn't missing out. So we've got 1, 0, 0, 1, 0, 1. L is 0, 0, 1. Right? And then E is 1, 1. So that would be the encoded message, right? Yes?
So for decoding, you just work in reverse?
Yep, that's exactly what, so I was going to say, suppose we got this message, right? Let's see. Suppose we got this message. 0, 1, 1, 0, 0, 0, 1, 1, 1, right? How would we, and I suppose so on the exam I'll ask you a question like this. Suppose you got this message, right? Decode it for me. Now the reason I give you a decoding message on the exam is so that you can get a nice English word out of it, and therefore check if you did your tree correctly, right? But if you decode it and it's gibberish, right, I'll still give you credit for the gibberish if that's what is accurately represented by your tree, okay? Right, the two questions are independent of each other, right? You're not going to get docked twice, okay? So let's go ahead and see. So 0, 1, that's P, right? So 0, 1, we ended up at P. Then, so now we got to a letter, so we start at the next bit. 1, 0. So we do 1, then we do 0. That's an A. So we got to an A. So we restart, and we're starting here again, right? Because we did 1, 0. We did 1. So we did 0, 1, 1, 0. And now we do 0, 0, 1, which gives me L, and then we do 1, 1. It gives us E, which gives us pale. Right? Let me tell you, it was a bit of a trick to find another word in that combination on the fly like that. So, okay, so that gives us pale. Okay? So that's a fairly straightforward. So once you get the trick of these are fairly straightforward. Please note that there will be a question like this, exactly like this, on the final exam as well as the exam. So be sure to be able to do this, because we do ask it on the final exam. It's always on the final exam because it's a fairly good knowledge just to understand how this works. Because the entire point of this is compression, to be able to make files smaller. Yes.
So the final exam is going to be just like the equivalent of 1068 or multiple choice?
Nope, no multiple choice. I abhor multiple choice questions on my final exam, and I am the writer of the final exam. So there are no multiple choice questions on the final exam. There are, that is both a good thing and a bad thing. The good thing is that makes it easier for me to write the exam. The reason we do multiple choice on 1068 is because we have an absurd number of students in 1068. And it just makes the grading a lot faster. On the other hand, it's a pain in the butt for the students. But here, we try to do 50-50 breakdown on this. All right. And besides, if it was multiple choice, they'd be multiple choice on theory questions anyway. All right, so coding questions now. So 2. I'm going to try to get these done so that you still have some time to work. So coding questions. Let me sit down and do this. So write a method which, given the root of a tree or subtree, computes and returns the number of nodes in the tree or subtree. You may not use the size method. Forget it even existed to begin with. Now, the reason I ask this question is because it's just a nice warm-up question for that. It's also a question I've actually asked the first time I taught 2168, so this is actually on the exam there. I since found a much awesomer problem because it comes with a story, so I can do that on the exam instead. But let's go ahead and see how this public static size tree would work. All right. All right, and let's zoom in so that the people in the back. I said zoom in, not out. Zoom in so that people in the back can see. Everybody in the back can see just fine. A bit more. Okay. So public static int size tree. So given the root of this tree or subtree. Remember, root doesn't mean root of the tree. Sorry, root of like this tree. It's especially since it's a static method. It's saying the root of some tree, right? Some tree's root, okay? Right, or subtree, right? It's a local variable named root, okay? It's just simply for saying it's any type, a tree of any kind, right? I could easily have done, I suppose I could have easily have wrote public static int node of anything, right? But I didn't want to confuse people with the syntax there. Okay. So, all right, public static int size tree. So, so first off, how do I calculate the size of the tree? This should be recursive, right? So first off, if a root is null, right? Then how big is the tree? It is then it is 0. Right? If the tree is null, return 0. Right? If there's no tree there, then there's no items to count. Otherwise, well, I'm again left in this situation where I've got a tree, and I got to figure out how big it is, right? And again, root. This is a completely local decision, right? So first off, we've got this node. It may or may not be the child of somebody else, right? Right, so this is root over here. May or may not be the child of somebody else. It has a left subtree. It has a right subtree, right? Or rather, it has a variable for a left subtree and a variable for a right subtree, okay? So, to calculate the size, what we need to do is we got to get the size of this side, the size of that side, add them together, then plus 1 because I count, right? Because I, the root, count. So let's go ahead and break it up into multiple lines. So int right is equal to size tree root dot left. Oh, sorry. Left, right. Int right is equal to size tree root dot right. Right? I was getting ahead of myself there. Okay? Get your left side, your right side, right? And then we can return left plus right plus 1. Now this, of course, is a post. I did this post order, right? Right? It could, I mean, it's, but again, it's addition, so it doesn't really matter, right? So, of course, I can also do this in one line by just saying, so I could do it in one line instead. By doing this. Return left. Sorry, return 1 plus size of root dot left. Yep, size tree root dot left plus size tree root dot right. Okay. So I could do that. I can also there's other ways you can do this. I just simply like doing this in one form, like in this set form, because it works for a lot of things. And the way I always do it is that I always assume the root is, I always have the assumption that the root is not null. Right, and that's just generally the best way to handle that. All right, so the next one is an interesting one that I'm very proud that I came up with, the isFull method. Right? And I'm proud I came up with this one because it's a test of, because we're using a method to test a property of a tree, right? Fullness or something like that. So that might be a subtle hint to you, and not so subtle right now, that one of the functions that you might have to write on the exam might have to do with testing a property of the tree, right? Writing some code to test a property of a tree. All right, so write a method which, given a tree, returns whether the tree is a full tree. This will be, and this was a hint here, this will be slightly different than the recursive traversal methods we've tried so far. And the reason for that is, well, first off, how do we know, what's the definition of a full tree again? Has zero, yep, so this subtree is full if not, so here's the key. It's full not only if it has zero, first, if it not only has 0 children or 2 children, but if it has 2 children, then if its children also have to be full as well, right? It's not enough for it to have just children, right? So common mistake there. So first, if tree is null, I have no idea actually right now, so I'm going to leave that blank, okay? I have no idea right now. I'm actually just going to write return null so I don't leave it blank. I have no idea there. I don't even know if it matters in this case, right? We just have to have something there. Could be return or true or false, but we'll figure out in a second, right? We'll leave that blank, but we know we need to have that base case, okay? So if it's not null, well, there's 4 possibilities, right? It has either it has 2, right? It either has 2 children, or it has no children, or it has 1 child of each. So let's go with the easy cases. If tree dot left is null and tree dot right is null. Right? If those two, if it has no children, is it full? Is this a full tree or subtree? Yep, it's full. We're done. Return true. Okay. So if tree dot left is not equal to null, so and tree dot right is empty, right? If it has one child on one side but not the other, then it's not full, right? It has one child. Return false. So we'll do the same over there for the symmetrical case. If tree dot left exists, but tree dot right does not exist, what? If tree, oh, sorry, yes. If tree dot left doesn't exist, but tree dot right does? No. Sorry, yes, other way around. Return false. And let's just go ahead and you don't need these else if cases. Well, at all. So these, if all these happen, then the implication is if we can make it over here, then guess what? You have two kids. Okay? So in that case, we need to return is full left, tree dot left, and if full tree dot right. Okay, so if my left subtree is full and my right subtree isn't full, null. But what if my and this basically, right, and this is why I kind of say I have no idea what to do here, because you're not going to call this. I'm going to go ahead and say return true here, because the only way this is going to be the case is that if your root is null, right? You're never going to hit this in any other case because, right, if one of your children is, if you have a null child, you're not going to call it, right? If you have a null child, that means that you have both null children or you have one null child, which means you're returning something. If both of your children exist, you're going to call them. Right? Make sense there? So we can just kind of, so in fact, you don't even really need this one over here too much. Right? Although it's best not to assume that it's null. What?
I don't understand why it would be false. If you just sent a node that was null.
If you I don't know, is an empty tree full? All nodes is an empty tree full.
It doesn't exist as a tree.
I mean, that's a question I don't bother asking on the exam, and that's a question that I leave to the mathematicians who do the theory behind this,
Okay.
right? Because is an empty tree full, right? It has no children. An empty tree would have all nodes have no children, and all nodes have two children. Okay, it fits the definition of a full tree, so I'm going to say yes. Yes.
Could you also keep the first if statement and remove the second if statement, because then the return statement would cover that case where the left subtree and the right subtree would have null?
I suppose you could in that point, right? There's plenty of optimization to be had here. Right, he's saying, if that's the case, can we just delete this? And the answer is, yeah, in that case we totally could, right? Because we say you either have one children or you have you have only one child, right? Return null. Otherwise, let's see, return true on my left, empty, empty, so that would return true. If I had
Based on that definition.
yeah, so that would work. Mm-hmm. So, does anybody else need clarification on this one? If so, I'm going to move on so that people. Yes. Oh, you're stretching. My bad. Okay, so I'm going to move on to the last coding question so that we can get done with this. I'm sorry, it's taking a bit more longer than I thought it would. Okay, but I'd prefer you guys to be plenty prepared for this exam, right? Here, this is from the previous question. This is from the previous exam, right? I think I've already covered this one in class before, the equals question, right? Notice that it said extra practice on it, right? So, and again, there's an extra practice question over here, but let's see. This is a lot like the question you got today, only it deals with a string rather than a list. But this is the type of question you're guaranteed to get onto your exam. So write a method which returns what characters occur in a string and then how many times each occurs. So for example, if you had apple, we would say A was once, P twice, L once, E once, right? So let's go ahead and write this one. All right. So first thing we need to do is make our map. Map character to integer, right? But if you're on an exam, you might be lazy and just do this, which is perfectly acceptable, right? Character map is equal to new hash map, right? Remember, you got to use a hash map, right? But again, if you're lazy, you might leave out the diamond notation, which is perfectly acceptable on an exam, right? Okay, so what do we have to do now? Well, we have to iterate through our string. So for each character letter in Word dot to-char array, I believe is the method there, to turn it into a character array. The other way you can do it, of course, is like do a for loop, right? For int I is equal to 0, and then you can use char at. But here I always prefer to use the for each loop. It's generally a better choice whenever you can do it. So for every letter in the word, if the map contains, let's go with contains key, right? I use the contains method when I write it, but I think technically it's the contains key method as it actually exists in Java. But I use contains when I write it just for simplicity's sake. So if map.contains key the letter, so if we've already seen the letter so far, so if we've already seen the letter, we're going to do something. So if we've already seen the letter, then let's see how many times we've seen that letter, right? So if map.contains key letter, that means we've already seen the letter. So let's get how many times we've seen it. Map.get letter. So we've seen it occurrences number of times. So now we've seen it one more time. So let's go ahead and update the map with that. Map.put letter occurrences plus 1, right? And as you saw on the quiz today, you can actually put that into one statement by just simply dropping, instead of occurrences, you can drop map.getLetter into there. And the reason I did it as one line because it was two reasons. One, it was one less line on the quiz, and also because I wasn't sure how to spell occurrences. Remember, I got my PhD in computer science, not in English. So, all right. So,
I got a question.
Yeah.
So, when you write the in occurrence, return an int, but the map.get
will return an int.
return an object.
It will return an object because so it's going to return an object because I didn't do this.
Oh, okay.
But as I said, on an exam, this is perfectly acceptable to leave this out since you're writing on paper.
Right.
Right. Those kind of things with casting I kind of just ignore because you've got a tired hand at this point, you know. Right? I'm trying to show you that most of these questions, right, they don't take too much time to write. Right? I don't have you write an essay's worth of code on this stuff. So otherwise, I did not see this. Right? If I've seen the letter, great. If I haven't seen it, well, this is the first time I've seen it, so map.put letter occurrences plus 1. So yeah, 1, my bad. Ugh. Map dot letter, put one letter 1. All right. Another way I've seen somebody do that, by the way, which was also pretty clever. Oh, and at the end, of course, return map. So another clever way I've saw somebody do this was if map dot contains key, right? If the map doesn't have it, so if it doesn't have it, map dot, this is a bit inefficient, but it was I thought it was pretty funny and clever in some ways. Put letter, so if it doesn't have it, put letter 0 in. And then map, then the next line was map dot put letter map dot get letter plus 1. And I just thought it was clever simply because it was shorter in terms of the amount of code that you had to write. Right? So what it says, if you haven't seen the letter, initialize it into the list. Right? You haven't seen it yet. So mark down that. And then over here, regardless of whether I've seen it or not, add 1. Right? So if you haven't, so this was clever because there was less code involved, but there was this little trick that had to be done first. However, you know, I only mention that because it's interesting to show little tricks like that, but when in doubt, be more direct about it. Okay. So now our last question, right? And this one is not the one that's going to be on the exam, but it's good practice for you. And so so email me that if you need to figure out, if you're having trouble figuring out the answer is that. But the trick here is that I'm giving you the category so you can create the categories in advance. So now on analysis, that will be worth 10 points. And each of those questions will be worth 5 points each. So what are collisions in hash tables? Why do they occur and how are they handled? So what is a collision first off? Yeah, when two keys, right? What?
When two objects hash to the same value and they want to go to the same spot.
Yeah, when two things. Do you want?
We can implement hash tables in arrays.
Yeah.
So what happens is when we try to place a value of key, which is an index in our array, and they try to go to the same index.
Right.
Then a collision occurs.
Right.
And yeah, we can try to address that either with open addressing, so it'll look for the next available thing, or we can do change, which links all the values at that.
Great. So that's great. That's correct, by the way. So yeah. So for everybody who didn't hear, when a collision occurs when you have object 1, right, and we put that into the hash table. It has a key, and we put it into some index of the hash table. And then we've got object 2, and we try to put that in the hash table, but it wants to go into the same index that object 1 had, right? You have 2 keys, right? All keys are going to be different, but they end up going into the same index because we keep our hash table smaller than the space of all possible keys, which is infinite, right? So since we don't want to have infinite space, there's going to be collisions somewhere, right? If you haven't seen the video yet, it's kind of the if you haven't seen the video on it yet, it's a parking lot analogy, right? If you've got a parking deck, right, that's 99% of the way full, right? It takes forever to park your car to find that spot, right? Every time where you try to see a spot and see if it's open, that's what we would call a collision in the hash table, right? However, if your hash table is 50% of the way full, or your parking deck is half full, right? Every other spot is open. It takes no time at all to basically find, oh, that spot's empty, but the one right next to it, that's pretty open, right? So it takes no time at all to basically get that. So how do they occur? So why do they occur and how are they? So we've covered why they occur. How are they handled? Again, there were 2 strategies. Open addressing, which simply says, oh, if I can't take this spot, I'm going to look for the next available spot. Now, there's different ways to define next. The way we've typically done it is linear probing. where next is defined as literally the next spot. Don't make it dumb, don't make it overcomplicated, right? So, so linear probing says, oh, if I can't go into index I, then I'm going to try I plus 1. If I can't have I plus 1, I'm going to try I plus 2. If I can't have that, so on and so forth. The other way to do that is like the other way to do open addressing is with quadratic probing, and that means, oh, if I can't have I, I'm going to try I plus 1. If I can't have I plus 1, I'm going to try I plus 4. If I can't have I plus 4, I'm going to have I plus 9. 1 squared plus 2 squared plus 4 plus 3 squared, which is 9, and then 16. The advantage for that is that it's a bit more spread out. Disadvantage is it takes a bit longer because you have to do a bit more mathematical operations. Not too much difference in runtime, though, in terms of open addressing, right? The other broad strategy that we've covered in this class that I don't really go into too much detail because it's very intuitive is chaining, where each slot doesn't actually have one item, it's a linked list, which can hold multiple items, right? So if you have a collision, you just simply tack it onto the end of the linked list. There's also other weird strategies like cuckoo hashing, which means that if somebody's in your slot, you kick them out of your slot and let them try to find another slot with a different hash, using a different hash function. And then that process repeats ad infinitum until everybody's happy. So then there's double hashing, right? You have a different hash function in case of a collision, right? So there's all different ways to try to resolve collisions, but the primary ones we focus on are open addressing. Now finally, what is the worst case runtime of insertion and deletion algorithms for binary search trees and why? It's O of n. Why?
Because it's a totally unbalanced, it's really linked list.
Yeah, because you could get a totally unbalanced tree, right? A binary search tree assumes that the tree is going to be balanced. If it's balanced, that means that every time we are looking for something and we go left or we go right, then since it's balanced, we no longer have to search for half the stuff. Half the nodes have been ruled out. If it's unbalanced, you're maybe ruling out maybe only a tenth or possibly only one node, right? Now, how do we get around that? We use in real implementations, we use a self-balancing binary search tree, which means if the tree detects it's unbalanced after adding or deleting an item, it rebalances itself in log n time. So operations always do take log n time. All right, so that's it for the practice exam.